Hi everyone, I'm Gil Hernandez, one of the front-end design teachers here at Treehouse. In this Treehouse workshop, we'll take a good look at ways we can speed up front-end performance, as it's currently one of the most critical components of a website or app. We'll be covering topics like why performance is important, ways to reduce HTTP requests, compressing our resources, browser caching, and much more. We'll also talk about tools we can use to test and analyze performance. So let's get started. So why is performance important? Well, the overall performance and speed of our sites or apps is something that we should always be thinking about. One of the main reasons is because it significantly reduces bandwidth usage. But mainly, it's more about optimizing the experience for our users. In fact, Google now uses site speed as ranking metric for its search results. So performance may actually be the difference between ranking on the first page or on the fourth or fifth page of Google. So faster websites are a lot less frustrating for our users, and they are perceived to be more interesting and attractive. So it's something that goes a long way towards encouraging repeat visits, especially now that people are more frequently on mobile devices. Performance is often more noticeable. Research has actually shown that user frustration increases when a page load time exceeds a certain amount of time without any feedback. So 47% of users expect a web page to load in 2 seconds or less. And 40% of users abandon a website that takes more than 3 seconds to load. And the number increases by about 7% every second after that. So it goes without saying that our visitors prefer fast websites. So we need to keep load times at a minimum and below these tolerable attention thresholds, because the average broadband user has very limited to no patience for pages that take too long to load. So how can we make sure our websites load fast enough to avoid some of these issues? There are a few things we can very easily implement in our sites to significantly improve load times. So here we'll talk about some of the low-hanging fruit we can quickly take care of. So first, let's talk about how browsers download page assets in a website or app. Every asset a page requires is an extra HTTP request, because the browser has to go off and get every single asset required to render a page. The more HTTP requests made to the server and the longer the elements take to render, the slower a website will be. So examples of HTTP requests are style sheets, scripts, images, and HTML files. So how can we reduce some of these HTTP requests? One of the ways is to maximize parallel downloading. We can also combine CSS and JavaScript resources. Another way is keeping those at imports to a minimum and using CSS image sprites. So let's go over each of these in more detail. So a browser downloads as many assets as it can from a single domain in parallel. The average is about 6. As soon as it reaches the maximum allowed on one host, the browser issues a request just for that number of resources and queues the rest. But we can get around this quite easily by serving resources from multiple host names. The more domains it can pull from, the more assets can be downloaded in parallel. But using too many of these connections can cause increased CPU usage, so Google recommends using between 2 and 5 hosts at the most. We can also serve assets from content delivery networks, or CDNs, which have powerful speed and technology that help decrease latency, because it serves the assets from suitable locations around the world. Waterfall graphs are also a valuable tool in helping understand how these resources load. You can, for example, see one in the Chrome DevTools under the Network tab in the Timeline column. We can also combine our JavaScript and CSS files into one file. A single larger CSS or JavaScript file will load quicker than multiple CSS or JavaScript files. Some sites, for example, may have a lot of plugins or features that can have a lot of extra CSS and JavaScript files. So it's beneficial to combine all of these into one CSS and one JavaScript file. In our CSS file, we also need to keep @import rules to a minimum, because @import rules requires the browser to download one CSS file before it can start downloading the others. They're not all downloaded at once with the style sheet load, so each one is a separate and rather expensive HTTP request that can increase the load time of the page. If we had to import another style sheet, it's usually best to link it from the head of the document, but more on that in a bit. Every image, whether it's an embedded image or a background image in our CSS, is a separate HTTP request. So if a lot of images like icons or logos are being served as separate resources, it can create a lot of overhead and may cause a significant performance slowdown. We can combine them into one image called a sprite sheet, and it will reduce the amount of server requests. So it's one large image that is made up of a number of smaller images. Each image in the sprite sheet can be used multiple times in different places. So it saves the overhead of having to load a bunch of images. We just call it once in our style sheet, then use the background image and background position properties to display them. Now, creating them can be a bit tedious, but there are helpful tools available that automate this process of creating sprite sheets. For example, spriteme.org is a JavaScript bookmark that loads on your page, then lists all the images found that can be grouped into a sprite sheet. It then creates and generates a sprite sheet along with the CSS needed to display them. Another simple and really effective thing we can do to speed up our downloads and reduce bandwidth is compress our text-based assets as much as possible to reduce their file size. We can do just that with minification and gzipping. Now, minification reduces the size of our resources with what are called minifiers to strip out any unnecessary characters like white space and comments in the code. Many times, we'll see a JavaScript file minified, but we can also do this with our HTML and CSS files. Some of the most popular minifiers for JavaScript are the YUI compressor, which can process both minified JavaScript and CSS. So we can download that at developer.yahoo.com/YUI compressor. We also have Google Closure Compiler, which is similar to the YUI compressor. It parses JavaScript, then rewrites it and minifies it. And next, we have uglify.js, which you can grab at github.com/mishwho/uglify.js. We can apply many of the same techniques we use to minify JavaScript towards minifying CSS, like collapsing white space and comments. Some popular tools for minifying CSS are CSS Tidy. We also have the UI compressor. There's also CodeKit and CSSminifier.com. Even for HTML, we can strip out the comments and white space. Some minifiers also remove things like empty elements, optional closing tags, and they collapse Boolean attributes and elements. Some examples of HTML minifiers are HTML minifier at willpv.com, and there's also the other HTML minifier at cangax.github.com/HTML minifier. The benefits of minifying CSS, JavaScript, and HTML are generally experienced only once for the user, because once these resources are downloaded, they're usually cached by the browser for the remainder of the session and future visits. Once our text files are minified, we can turn on compression with gzip. Gzip compression finds similar strings within a text-based file, then temporarily replaces them to make the file size smaller. Some of those repeated strings are things like white space, tags, and style definitions. So the more of those matching strings we have, the more our files will be compressed. It's important to consider gzipping because it can actually reduce our files by up to 70%. So it's a big performance gain right there. For gzipping, we can use tools like gzip.org. Also, the HTML5 boilerplate has some useful .htaccess code for gzipping. And since gzipping works well on text-based assets, that means that we can even gzip SVGs and other certain font file formats. So images are one of the biggest resources that can affect a page's performance, and there can be a lot of unnecessary data being transferred in images. Proper image compression can make a big difference, but we need to be careful with the way we compress images, because a lack of understanding of the different compression types for images can result in images with larger file sizes and images that don't look as good as they should. So for example, the JPEG is good for photographic images with many colors or gradients. With JPEGs, there's usually a trade-off between image quality and file size. So for example, a quality of 0% is the absolute lowest quality, while 100% is the very best, but it's the largest file size. You typically want to keep your JPEG compressions between 60 to 80%. That seems to be a pretty good middle ground. GIFs are mapped to a color table containing up to 256 colors. And when we export a GIF, each pixel in the GIF is then replaced by a number that represents one of these 256 colors. But the color table itself is never preset with certain colors. It actually allocates the colors from the image being used. So for smaller images with only a few distinct colors, a GIF would be the ideal format. PNGs, or PNGs, can be used as a replacement for both JPEGs and GIFs. One of its biggest advantages is that it supports transparency via an alpha channel, which is way more advanced than the binary transparency the GIF supports. Now, PNG handles images and graphics extremely well and can be 5 to 25% more compressed than a GIF file. So the SVG format is a different approach that uses XML to describe how a graphic should be drawn by the browser. And it contains information like the dimensions of polygons, fill colors, strokes, and a lot more. We can also create things like gradients, blur effects, drop shadows, and filter. So they can be an alternative to the other image formats we just covered because they may sometimes result in smaller file sizes. And most importantly, they are completely scalable and can be resized without affecting quality. But the larger the file in XML, the more that needs to be parsed and drawn by the browser, so it can raise some performance consideration and in some cases be slower than displaying a JPEG, GIF, or PNG, especially if we add some of the gradient and filter features. But like I previously mentioned, since they are technically text-based assets, we can gzip SVGs in production to reduce the file size, or we can compress them and convert them into data URIs. Since JPEGs, GIFs, and PNG graphics already use some form of compression for the web, there's really not much to be gained by applying some of the content compressions we would with text-based content, like CSS and JavaScript. The reason why is because those extra compression methods can actually make image files larger and it wastes CPU cycles. So let's talk about some other image optimization tools we can use. Since properly optimizing images can drastically improve loading times, we can use other optimization tools that use various compression options and also help remove unnecessary metadata from images as well as optimize the use of colors. So one of these tools is tinypng.org, which uses advanced compression methods for PNG. CodeKit's image tool can also reduce JPEG and PNG file sizes with just a click of a button. There's also pnggauntlet.com and imageoptim.com. With that, we can just drag and drop images or an image folder into a window, and it will find the best compression parameters for each image. Now, there are more rendering methods we can use for JPEGs. So perceived speed can sometimes be better for our users than the actual file size of an image. So an image that is actually larger in file size but appears to be loading faster will oftentimes be more effective in terms of usability and the perception of speed. For example, JPEGs by default use a baseline compression method. So in this method, the data of the image is compressed from top to bottom. So when the JPEG loads in the browser, it starts rendering from top to bottom. Now, if it's a large file or if the connection is slow, we can sometimes see this unpleasant effect where the image slowly loads from the top down. So I'm sure we've all seen this at some point. But there is another compression method we can use known as progressive compression. With progressive compression, the JPEG loads through multiple passes of the image. Each pass produces a higher detail in the image. So when it first loads, the image starts out blurry, then gradually becomes more detailed until it entirely loads. So for someone with a slower connection, this can be a good thing because they can see the rough image right away instead of nothing or a partially loaded image. And the user gets feedback that something is going on, and it gives them that perception of speed. On average, progressive JPEGs tend to be smaller in file size than baseline JPEGs. For JPEGs over 10K, the progressive compression will actually give us a better compression 94% of the time. So that's pretty good. There is a progressive compression setting we can check off in Photoshop in the Save for Web setting windows. We can also consider using icon fonts instead of images. In a test done by Pictonic, they concluded that an icon font can load as much as 14% faster than an image and can be as much as 90% smaller than an SVG file. So that is pretty remarkable. And of course, we can take advantage of CSS3 features like gradients, multiple background images, drop shadows, border radius, and a few other properties, which are now supported by all the major browsers. So let's talk next about ways we can boost JavaScript and CSS performance. So first up, we should place all JavaScript files at the end of our HTML document, right before the closing body tag. Doing this defers the parsing of JavaScript. JavaScript that is loaded towards the top of an HTML document slows down a page because it blocks the browser parsing of the page, and it interrupts the parallel loading process. So it's better to call them at the end of the document. That way we allow the visible elements to be loaded before the JavaScript, which makes the page appear to load much faster. We can also use what are called JavaScript asynchronous loaders, which not only load JavaScript after everything else has loaded, but also the execution order of our scripts. So we can, for example, load script libraries like jQuery in a modular way instead of having to load the entire library. We can then trigger jQuery plugins accordingly. Now, some helpful script loaders are Require.js, there's Lab.js, and you also might want to take a look at YepNote.js, which loads scripts conditionally based on any statement that can be evaluated to either true or false. Unlike JavaScript files, it's best to include links to external style sheets in the head of the document. Browsers delay the rendering of a page until all CSS has been downloaded to avoid repaint or redraw of the page. This way, we avoid unnecessary reflows and repaints by the browser, as those can actually be quite expensive. A repaint happens when any changes are made to an element that changes its visibility, but not its layout. So for example, adding an outline to an element, or changing the visibility value, or even changing a background color. Page reflows are more critical though, because the changes made affect the layout of a page. Whenever an element is reflowed, it causes the reflow of all its child and ancestor elements, along with any other elements following it in the DOM. It's like the equivalent to laying out an entire page again. Now, there are ways to minimize these reflows, but first let's talk about what may cause a reflow in a page. So reflows are caused by resizing the browser window, changing a font size, width, or height in an element, the padding as well. Using the display property, for example, display none, can also cause reflow. Even content changes like typing text in an input box can cause some form of reflow. So what can we do to minimize some of these reflows? Well, in some cases, one thing that can help is specifying the width and height dimensions of embedded images in image tags. This allows the browser to reserve space for the image even before it has downloaded. So we can add the dimensions in either the HTML tag or in the CSS. A change deep in the DOM tree may also require a change all the way up to the parent element or down to the children and nearby elements. So every level of hierarchy we add causes more time used for reflow. For example, avoid making a style change to a parent element when we know we'll only need to style child elements. Target that child element instead because minimizing that DOM depth is important. We should make our selectors leaner and more performant by cutting out the unnecessary bits. Complex selectors require more CPU power to do selector matching, especially with descendant selectors, as they are one of the most expensive selectors in CSS because browsers have to parse a lot of selectors and elements. Browsers parse selectors from right to left. So in this rule, for example, at least 3 of these selectors are unnecessary. The browser first has to look for all anchor elements, then check that they're in an element with a class of content, then if it's in a class of wrapper, and so forth, all the way up to the HTML tag. So this causes the browser to do a lot more work than it needs to. So it uses up a little more load time. We could instead cut it down to something like this, or sometimes we're just better off creating a class than having these overly specific styles. Even though performance on smaller sites likely isn't always noticeable, it's still good to keep an eye out for these kind of things. At least it makes our CSS more efficient because nowadays inefficient CSS is also a strain on development resources and maintenance, probably more than it is on performance. When using CSS animations, they can have complex rendering changes. So it's best to render these animation changes out of the flow of the content. And we can do this by using a position of absolute or fixed on the element, because it won't affect the layout of surrounding elements. A more efficient way to use animation is using the translate property instead of the top, left, right, or bottom offsets, so that their positions, width, or heights won't be affected. This provides hardware-accelerated animation by elevating the element onto its own render layer on the GPU. So any transforms or opacity changes will be offloaded to the GPU and will result in faster performance. Another thing that can increase performance is prefetching. Prefetching is an HTML5 feature that enables the loading of pages and resources before the user requests them. The browser can download them ahead of time, and it cuts out a lot of the overhead involved when downloading pages and resources. Now, there are a few types of prefetching, but here we'll go over DNS prefetching and page prefetching and pre-rendering. Some browsers support DNS prefetching of links, which hint to the browser that a user will be requesting some additional resources from a certain URL. So it allows the browser to cache the DNS call. We can use a link tag to identify the domains that the browser needs to resolve ahead of time with a rel attribute of DNS prefetch. DNS prefetching is currently supported in Chrome, Firefox, and IE9 and above. With page prefetching, we can hint to the browser that a page should be prefetched in order to speed up the browsing experience of users. We can do that with a link tag and an attribute of prefetch. The browser then fetches the top-level resource of the URL we specify. Now, pre-rendering extends the concept of prefetching. It not only downloads the page, it also downloads all the resources in the background as if the page was being displayed by the browser without actually showing it until the user clicks to it. Now, from a user perspective, the page loads much faster. We can trigger pre-rendering by inserting a link element with a rel attribute of pre-render. Pre-rendering should only be done when we have high confidence in which link a user will visit next. So, for example, the read more or click to next page link in a main article. Our site analytics can actually be helpful in determining this for us. The downside, however, is that if we prefetch or pre-render too many assets or pages, the browsing experience may suffer and increase bandwidth. And since it's actually preloading pages and assets, it can also skew our site metrics. But again, site analytics can also give us valuable clues as to which page we might want to prefetch or pre-render. That way we'll know which resources the browser is likely to need the majority of the time. So we know that every HTTP request has an overhead associated with it. Caching stores our resources in a temporary local location to improve performance. So it's much faster to load a resource from the local cache than to do another request to the server over the network. This is good for static files like CSS, images, JavaScript files, and so forth. It's also said that an estimated 40 to 60% of daily users of our sites will not have resources cached in their browser. So making our page fast for these first-time visitors is a key to a better user experience. So for example, with browser caching, we can ensure that our assets have expire headers that instruct the browser to load previously downloaded resource from our local disk rather than over the network. To enable an expiry date or a maximum age in the HTTP headers, we'll need to add the expire headers to our htaccess file. The HTML5 boilerplate has some default .htaccess code we can use just for that. So you can check it out at html5boilerplate.com. Like I said, caching works best with static files. So this means that we need to be careful with caching HTML files because those are typically not static and shouldn't be considered cacheable. But say we make a change to our CSS file and want to break the cache by appending version numbers, such as v1 or v2, to their file names. This allows us to aggressively cache it and manually force a cache refresh whenever the file is updated. So finally, let's take a look at tools we can use for testing page load times and analyzing web performance. So first, the Google PageSpeed tools have a lot of powerful tools that help us identify those best practices for performance. They also have an extension for Chrome and Firefox that evaluates performance, then gives suggestions on how to improve it. You can check that out at developers.google.com/speed. Google also has Speed Tracer. It's another great tool for identifying performance issues that we can also use as a Chrome extension. Finally, we can also just use the developer tools available in browsers like Chrome and Firefox. For example, the Network tab in the Chrome Developer Tools can be really useful for identifying those larger files that take a long time to load. And we can see this in their timeline waterfall view here. The CSS and JavaScript profiler under the Profiles tab is also great for finding those greatest offenders in our style sheets and JavaScript files. Finally, the Audits tab is also good for finding unused CSS in the current page. We can find those under the Web Page Performance panel after we click Run here. And there it is. So that'll do it for our front-end performance workshop. I hope you now have some knowledge and tools to begin analyzing and optimizing the front end of your website or app. To learn more about CSS performance, HTML, and JavaScript, check out our learning adventures on becoming a web designer or developer and our deep dives on HTML, CSS, and JavaScript. I'm Gil Hernandez. Thanks again.